Thank you everyone for coming to our webinar today. Calculating tonnage, understanding force requirements for precision cutting, given by Zach Haddock. It'll be about a 20-minute presentation, 15-minute question and answer. If you have some questions, you can submit them via the Q&A button at the bottom. This session is being recorded, and we will send out the presentation next week to everyone who has registered. The agenda for today is what is tonnage, how tonnage is defined, benefits of accurate tonnage, roller presses, and tonnage testing and formula. Your speaker for today will be Zach. He is a lifelong Kansas native. He has his bachelor's degree from Pittsburgh State University and has been with Preco for many years, since 2007. He is our flatbed and rotary salesman for the electrical, and laser, I should say, for the electrical area, and he can often be seen in our text tips section of our videos. Zach, I'll let you have it.
Yeah, thanks, Quinn. As always, appreciate the introduction. Looking at the attendee list, I see quite a few familiar names, but also see a whole bunch of new ones. So welcome, everyone, and I appreciate you all joining us today. So this talk, we're going to talk about tonnage and what the advantages are of being able to vary the tonnage and how we calculate how much tonnage we need. So first question would be, what is tonnage exactly? Well, in the most simple of terms, tonnage is the force in pounds or tons required to cut through the material. You know, it's a little bit of a misnomer that we are cutting material. We're actually not. We are putting such an enormous amount of force behind a very small cross-section of that cutting rule that the material actually fractures or bursts. And that takes quite a bit of force to get the materials to do that. Some materials more, some materials less. But there's some distinct advantages when we are processing materials to only the optimal amount of tonnage. And we're going to talk about that today. But the first step towards that is figuring out how much tonnage do I need for a given material. So how do we define that tonnage? Again, tonnage is the force in pounds or tons required or delivered during each cutting stroke in the press. Now, it's a little bit different. We're going to be really focusing on flatbed applications here. But in the instance of rotary die cutting, we really don't concern ourselves with calculating tonnages. And it has to do with the cutting action of the rule. So if you look at the upper image there, that is a depiction of basically a circular punch coming down on a flat press. And all of the force, all of that tonnage is equally distributed across the entirety of that rule. So if you think about it in terms of you're cutting your Christmas cookies, you're pushing that cookie cutter through the entirety of the dough in one swift push. Whereas when we're rotary die cutting, it's a little bit different. That force is being applied to a much smaller cross section of the rule because we are cutting in a tangential fashion, meaning that only bottom dead center on that cutting die versus top dead center on the anvil is in contact with the material. That force gets extremely, extremely focused. Theoretically, if your bears are closed on a rotary die, when it hits bottom dead center, you have theoretical infinite tonnage. Now we know that's not true. Metal stretches, flexes, bends, but you have an enormous amount of tonnage. So we don't really typically worry about calculating it in the instance of a rotary. We do monitor it because we can see when tools start to wear out. But it usually doesn't play into our plan of having to calculate it. But the total required tonnage, that equals the sum force needed for the cutting rule to compress the ejection rubber and then fully penetrate the material. The compression of the ejection rubber, that's an important part that we're going to need to keep in mind as we move through and we do our calculations. So what are the benefits of having an accurate tonnage? Well, it can increase your throughput. It can improve your cut quality and make it more repeatable. And then it also, if we're doing what I like to call delicate processes or delicate die cutting, we can kiss cut down to very thin, very delicate liners, is if we're using just the required amount of tonnage and not going more, because there's such a lower shock load or shock wave, I should say, when that valve shifts or when the tonnage is released. We gain throughput, and you'll see the graphic there of the cup of water filling up and down. Everybody's probably asking themselves, what is this? Think of it in terms of this. Let's say that cup represents a 40-ton press, and the filling of the water is the building of the tonnage. So if we fill that cup at a steady rate, it takes much longer to fill the cup completely to 40 tons than it does to fill it halfway to, say, 20 tons. So you will gain some throughput in the cycle time on the system. Now, we need to point out that we are talking about milliseconds. Milliseconds on every stroke of the ram over a large run, say we're going to do tens of thousands, hundreds of thousands, or millions of parts, milliseconds adds up to a lot of gained throughput. The flip side of that coin, though, is on a short run, say we're just running a few hundred, maybe 1,000, maybe the juice isn't worth the squeeze in that instance of maybe it's not worth going through all of the steps required to change the tonnage or to even calculate it. So usually my recommendation is with short run job shops where you're turning and burning a bunch of different jobs, we don't really worry about varying the tonnage, but on long runs, it absolutely will make big gains for you. So they're on flatbed dies, and the reason that I bring this up and want to show it is because there is a type of flatbed press called a roller press. And this is kind of my graphical depiction of what that is. Essentially, it's the same steel rule die that you're going to use with a hydraulic, clamshell, even a clicker press. But the cutting action is much different. There is a large steel roller that effectively rolls across the back of the die, just like you see right there. And again, much like with the rotary application, all of that force is being applied bottom dead center of that roller. So the force is concentrated. So yes, our tonnage calculations come in a little bit, but typically on a roller press, we're not too worried about it because you've got, forgive me for the pun, a ton of tonnage there to begin with, just from the nature of how it operates. So how do we determine, this is the kind of beginning steps of how we determine how much tonnage we need for given a material. Typically what we would want to do if we really want to get brass tacks and figure out exactly how much force is required on a given material, we would do a tonnage test. Now, the simplest way to do a very accurate tonnage test is to just use a simple arbor press, a load cell, which you can buy load cells off Amazon or McMaster Carr, Granger, all of those places, and then have a small die made with a known amount of rule. So say like a 1x1 square. We know we've got 4 linear inches of rule in that square. What you can do is you can put it in the arbor press and you can actually measure the amount of force it takes to cut that material with that known amount of rule. And then it becomes very easy to extrapolate that particular material, what the pounds per linear inch is. Now, we don't always do that. It's actually kind of a rarity that we would go through the exercise of really nailing it down, but we would be looking for some very specific outcomes if we did that. In general, we'll just use some kind of general numbers to cover us over a wide gamut of materials, and it tends to work pretty well. So for open cell foams, usually you can bet that they're going to be somewhere 200 pounds per linear inch or less, typically even sometimes less than 100 pounds per linear inch. I was just running some material for a customer about a month ago. Believe it or not, it was less than 20 pounds per linear inch. You almost could drop the die on this material and it would cut. Closed cell foams, a little bit more. They're a little bit more dense, so that increases the amount of pounds per linear inch we need. Those typically run somewhere between 200 and 600 pounds. Plastics are also somewhere in that 200 to 600 pound range, depending on the plastic and the density. And then abrasives, those really start rocketing up. It is not uncommon, say for an 80 grit abrasive sanding paper, to be over 1,000 pounds per linear inch. This is also true of gasket materials that might have steel scrims in them and things like that. It makes sense. Essentially, when we're cutting abrasive, we are cutting rocks. So it takes a lot of force to get through that. But you can see how those numbers start to add up. We've only got so much die rule that we can put in a press given a certain material. So once we know how many pounds per linear inch a given material is going to take to cut, we need to know how many linear inches of rule we're going to have. Now, the easiest way to figure that out is just with good old CAD. SolidWorks, DraftSight, AutoCAD, they all have a simple function that will tell you what the perimeter is or what the linear inches of a given line is. That is the most accurate way to calculate it. You'll see I've got a bullet note there that says make sure you capture everything. It's very common, very easy, especially if you've got more of a complex geometry, to add up all your rule but forget your punches, especially if you've only got a couple punches in there. Every bit of the cutting rule, punches and or steel rule and or Chemetch rule and or machine die rule, that all needs to be accounted for. Again, CAD's the easiest way to do it, but sometimes you just got to get down and dirty, and maybe a ruler. You might have to break out the calculator and do some do your circumference calculations on your punches. But once we have the total linear inches of rule, then we can start plugging numbers into our formula to figure out how much tonnage we need. And the formula is pretty simple. We've got linear inches of rule times our pounds per linear inch divided by 2,000, which gives us tons, and then that gives us our required tonnage. So you would see that if I've got a die that has 137.35 inches of rule, I multiply that by 400 pounds per linear inch, divide that by 2,000, I get 27 tons. So that particular die, given the material I'm cutting, I only need 27 tons to cut. If I'm on a 40-ton press, essentially I'm saving roughly about a little over 10% of my, or I'm sorry, 20% of my cycle time just by running the minimum tonnage or the optimal tonnage. Now, there's a specific reason I put 400 pounds in there. It is very common and nothing wrong with it, widely accepted, to do what I call the shoot from the hip. We are not always in a position to go out and do a brass tacks tonnage test. 400 to 500 pounds per linear inch is kind of that meaty part of the curve. It's kind of the mean of the average, or the mean of all the numbers. If you use 400 to 500 pounds per linear inch, and then use my 80% rule, which we're going to talk about, you will be in the ballpark for most materials. Most materials. You've got to bear in mind, though, when you've got the kind of outliers like the abrasives, the steel scrim, gasket materials, things like that. But in general, just for general quoting, ballparking, hey, do I have enough press for this? 400 to 500 pounds per linear inch will work for you. We can't forget our ejection rule, our ejection rubber, though. That also is going to soak up some tonnage. So it's frankly a little bit easier to calculate than our linear inches of rule. We're just looking for area. If you've got a full rubber die like this is represented here, where you basically just have a big block of rubber, all you have to do is measure the length and the width, multiply that by the density of the ejection rubber. That can be found on the spec sheet. That can be found by asking your die maker. Common ones though, 25 PSI, 45 PSI, 90 PSI. 45 is by far the most popular. That's what you're going to see on the black and gray rubbers that you see on most dies when they come in. 90 PSI, that's your green gorillas, red rhinos. 25 PSI, that's some real specialty stuff. You don't see a lot on the lower end. But it's as simple as calculating your square inches, multiplying it by that density, divided by 2,000, and that gives you your tonnage. So you can see in this instance, I've got 2 tons just on my rubber. So all I have to do is plug that in or add that to my tonnage for my rule, and I've got my optimal tonnage for running that press. Let's talk about machine capacity and that safety margin. That is my 80% rule. Okay, so what I mean by the 80% rule is I don't like to soak up more than 80% of the available tonnage on my press. The reason for that is if I'm doing that shoot from the hip calculation, I'm usually not figuring in the ejection rubber. So I'm relying on that extra 20% to make up for that. If I am doing the brass tacks calculation, we're getting down to it. The reason I still want to leave that 80% utilization of my tonnage, that 20% safety margin out there, is because I need to account for tool wear, and then I need to also account for some ejection rubber. The tool wear, as the dies get dull, and they will, all dies are going to get dull. As they dull, that pounds per linear inch is going to go up. And so we need to make sure that we account for that. There are times we've got to be honest with ourselves. There are times that we are running a press near the max, and that's fine. You can run a 40-ton press for the next 40 years. It's not going to hurt it. It's designed to run at that tonnage. The reason that we don't want to run at maximum tonnage, or max out our available tonnage, I should say, is because we could end up with parts that every now and then are partially cut, or they may stop cutting altogether as the die wears. So we really want to make sure that we've always got a little bit of a safety net there, a little bit of a safety margin. So as you can see, it's really simple to calculate tonnage. There are some real advantages in throughput, your ability to do delicate processes. The other side of it is one of the bonus sides makes the press cycle quieter too. And in the instance of, say, like a male-female die, you can actually switch the press to run off position, and it will automatically run on minimum tonnage for you. And in that instance, your throughput goes through the roof. So I hope you all learned a few things from this. I'd certainly appreciate you listening to me, and I'd like to open up the floor for any questions anybody might have about tonnage, dies, or materials.
Perfect. Thanks, Zach. We do have a couple questions. I'll start with the first one. Why do you try to stay at no more than 80% utilization of available tonnage?
Yeah, so that goes back to it's a safety margin. And, just like bridges are engineered with a safety margin in them, the rated max on the bridge, might be, I'm making up numbers, could be 100,000 tons. The bridge is actually engineered to go higher than that. It's a safety factor. And that's the same reason I don't like to go over 80% of my available tonnage on the press. It's to catch all the unknowns. There's a lot of variables going on when we are setting up these presses: die wear, ejection rubber wear, all of the above. The fact that maybe we just miscalculated a number. If I've got that 20% there, that usually will cover me in all instances, especially if it's a hot job and I've got to make sure I've got to get it out the door.
All right. Does the rule type affect tonnage?
It does. It does. And that would be an instance where we probably would want to do a brass tacks tonnage test. And when I say brass tacks, I mean we're really getting down and honing in on the values and the numbers, the variables. But just as a for example, if you've got a combination die where you've got a standard center bevel rule, but you've also got some creasing rule in there, that creasing rule is soaking up an enormous amount of tonnage. And you need to account for that. The same if you were running a serrated rule or a perfing rule, they all are going to have, given the same material but different rule, they're all going to have slightly different pounds per linear inch values for cutting. So the rule type absolutely makes a big difference. And I will preface that my 400 to 500 pounds per linear inch kind of shoot from the hip, that's really just based off of your center bevel or long center bevel rules. It kind of goes out the window if you've got any creasing rule, any big rule like 6 point or larger, anything like that.
Okay. How about an unbalanced die shape or multiple different shapes in one die?
That is a fantastic question. So an asymmetrical die or an unbalanced die, it really doesn't affect how you calculate the tonnage, but it will affect how you balance the die. And this is more of kind of a general setup thing. When you've got an asymmetrical die, so I'm trying to think of like a common shape everybody would know, but let's just say you've got a shape of a bunch of balloons and then one string coming down. Up top where all the balloons are, there's a bunch of rule up there. And then where the string comes down, where the balloons are tied together, there's not much rule at all. That die, the load on it as it comes down is going to try to shift the die to one side. It's going to try to kick it over actually towards the string side where there's not much rule. So you have to balance that die out in order for it to cut correctly or to cut efficiently. And the way you would do that is by offsetting the amount of rule with denser ejection rubber. And the cool thing is once you figure out what your pounds per linear inch to cut is on that rule, it gets pretty easy to calculate how many square inches of dense rubber you need to equal it out. So what I'm getting out of it is we may have a softer rubber over on the side of the die where we've got all that rule, but on the side of the die where we don't have much rule, we have a more dense rubber, and it equalizes it out so that the die comes down flat and it doesn't offset or load the press.
Thanks, Zach. Can you make up more tonnage with dwell time?
Not really. No, you could make the argument that maybe there's some softer materials, or there's always outliers. There's always fringe materials that, take maybe a little bit extra time. But in general, if it hasn't cut, it's not going to by the time the ram cycles. The other side of that is, and you need to be careful with it, is if you've got a press that is capable of dwell, you need to make sure that it's capable of an active dwell if you're going to try to do that. Because if it's not an active dwell, meaning that it's holding that tonnage down, it's essentially just coming down, then bleeding off all the pressure anyway. So in general, no. Are there some extenuating circumstances? Yes.
Great. Last question. So if anybody has any more, can I use pin ejectors instead of ejection rubber in a die?
Sure, absolutely. There's nothing wrong with that. And basically at that point, depending on how many they are, it's still pretty easy to calculate how much tonnage they're going to take up. It's just the whatever the spring rate is on the spring puncher, or sorry, spring ejector. And that becomes pretty simple. How many do you have? What's the spring rate on them? But yeah, those are absolutely fine. You don't see them a lot in flat dies just because they tend to leave witness marks on the materials. That being said, There are some when you've got very small, narrow traces. And when I say traces, sections of material where the rule is really close together. There's some instances where you just simply can't get ejection rubber in there, so you'll have to use some sort of spring ejection, and or it's a heated die that's being heated up really hot, and the ejection rubber just can't take the heat. So you've got to put a spring ejection into it.
All right. How much does the adhesive liner affect tonnage?
The adhesive on the liner, so like if you were kiss cutting a material, it doesn't tend to, it would be negligible. I would say it's lost in the noise as far as your calculations go. The adhesive, most adhesives are fairly elastic, fairly liquid. Um, it's so minuscule it doesn't even really become part of the equation most of the time. The adhesive, though, will have an effect on how you rubber the die, and how you rubber the die will have effect on tonnage. So in that instance, yeah, there is a kind of tertiary connection there, but in general, not really.
And he did clarify kiss cutting versus cutting through. So
Yeah, either way.
okay. All right, one more. Can I just run full tonnage all the time?
Absolutely. And there's nothing wrong with it. I make a pretty strong, I feel like I have a pretty strong argument that if you're running, if you're doing a lot of job changeovers during the day, say, 4 or more job changeovers throughout the course of a day, it's not worth going through the exercise of changing the tonnage. Just run the same tonnage, do your changeover as quick as possible. If you're doing a long run, days where you got the same job on there, absolutely go run with optimal tonnage because you're going to save a lot of time. There's a trade-off of how much time do I spend setting the tonnage, and I should say setting the tonnage correctly on the press versus just getting it on there and running it, getting it off. Because at the end of the day, we're talking about milliseconds every cycle. So it does take a certain number of cycles for you to see a market savings on that cycle time. Sometimes it's incredibly apparent. You might gain as much as 5 to 10 strokes a minute. Especially if you were running at 40 and you find out you only needed 7, you're going to see a significant increase in throughput. But at the end of the day, if you're doing a bunch of job changeovers, it probably just run full tonnage. And we have a lot of customers that just run the full tonnage. There's nothing wrong with that.
All right, that was our last question. So if anybody has any more, I'll give you just a minute to submit them. If you have any questions that you think of later and would like answered, Zach's information is still on the screen here, and we'll send out an email to you guys as well with that information that you can reach out to Zach anytime needed if you have something that you want answered.
Good.
So I think that's all we have today. So thank you, Zach.
Thank you. Those were excellent questions. I appreciate everybody's time, and don't hesitate to reach out to us.
Thank you.